Okay, so yeah, may I have your attention please. So, we were looking at wave and traversal algorithms in the last class. Just let us quickly recap what we were doing. So, we described a wave algorithm as an algorithm which satisfies three requirements, namely each computation is finite, each computation contains at least one decide event, and in each computation each decide event is causally preceded by an event in each process, right. And then we looked at another class of algorithms which we call the traversal algorithm. It is an algorithm which has the following three properties, that is, in each computation there is one initiator which starts the algorithm by sending out exactly one message. A process upon receipt of a message either sends out one message or decides, and the algorithm terminates in the initiator, and when this happens each process has sent a message at least once, right. Now, so what is the difference between these two types of algorithms? What is the difference between wave and traversal algorithms? How are they different?
Number of messages sent. There is some ordering in traversal algorithms.
Exactly, that is a very good answer. See, traversal algorithms are a special class of wave algorithms. They are not different algorithms, they are a special class of wave algorithms. What is the difference? In a wave algorithm, if you go back to the echo algorithm, you will see that the messages are sent out in parallel, right. So, when one node propagates its messages to its neighbors, the neighbors in parallel send out messages to their neighbors, right. So, if you look at all the messages that are floating about, they are not all causally ordered. In other words, that when I send a message to you and you, right, then your sending of messages do not have any causal dependency. So, you independently send your messages to your neighbors and he independently sends messages to his neighbors. There is no causality between those messages, right, though both of them are causally dependent on the original messages that I sent to both of them, right. So, they all depend on the initiator, they causally dependent on the initiator, but between themselves they may not be causally dependent. On the other hand, in a traversal algorithm, at a time only one message is moving around, right. So, it is going from one node to another, from that node to another, the token is getting passed like that. So, every message, so the messages are totally ordered, they are totally ordered in the sense that given any two messages, one is causally dependent on the other, right. So, this is the difference between the wave and traversal algorithms. Now, we were looking at yes.
Is it necessary that it should reach to every node before it decides?
Yes, that is because that in the wave algorithm you look at the last condition, that in each computation each decide event is causally preceded by an event in each process, right. So, therefore, every process has received the wave and has done something, and the termination or the decide event is causally following all of those events, okay, right. And it is the same in the traversal algorithm also, because traversal algorithm is a special case of a wave algorithm. So, the algorithm terminates in the initiator, and when this happens each process has sent a message at least once, right. So, because traversals are special cases of wave algorithms, so that same the wave properties also hold on the traversal algorithms. In addition, the wave algorithms allow partial ordering among the messages. In the traversal algorithm, there is a total order among the messages, okay, that is the main difference. Now, as a consequence of the fact that every message is totally ordered, the number of time steps or the time complexity of the algorithm of a traversal algorithm tends to be more than the time complexity of the wave algorithm. So, for example, if you look at the echo algorithm, then the echo algorithm will go out in d number of steps, where d is the diameter of the network, and then the wave will recede, right. So, the number of time steps will be of the order of twice d. On the other hand, when we looked at the distributed depth first algorithm, which is a traversal algorithm, there we saw that the number of time steps can be order of 2e, where e is the number of edges. Now, that is not linear in the number of nodes, right, because e is typically quadratic in the number of nodes. So, we spend a lot of number of time steps to execute the traversal algorithm. Okay. Now, we will see some improvements over the classical depth first search algorithm, by which we can reduce that amount of time. Okay. Now, before we do that, let us quickly go through the depth first search algorithm once again, the distributed depth first search algorithm. So, the initiator starts the algorithm by choosing some neighbor of the initiator and sends the token to that neighbor. Okay. When a process receives a token from a neighbor q0, then it does the following thing, that if this is the first token that it has received, then it identifies q0 as its father. Okay. And then it checks whether every neighbor is already visited, in the sense that is used p q true for every neighbor q. If so, then it decides, all right. Otherwise, if there is a neighbor q, okay, such that q is not the father of p, but that neighbor was never used before, what does this mean? It means that it is getting the token back along a front edge. Okay. Why? Because q is a node which is not used, okay. It is not used, so I have not sent the token to q ever, and q is not a father. Now, if you get the token from that node, then we will just send the token back to that node, all right. And otherwise, we will choose any neighbor except the father which is not yet visited, and I will send the token to that neighbor, all right. And then when I find that other than the father all the other neighbors have been used, then I will send the token back to the father, right. So, who executes this decide? Which are the nodes which can decide? Can a non-initiator reach this statement? Yes. You see, for all non-initiators, the father is never used, right. So, the father is never used. The father, see, for all non-initiators, the father is used only here at the end. Okay. Every time before that, the father is never used, right. So, which is the node which will see that all its neighbors are used? Is only the initiator, and the initiator will decide. Okay. Now, so what is happening? Let's look at the scenario. I will show you a very pathological situation and we will see how to get around that. So, let us say that these are our nodes. Now, let us do a depth first, let us see how the distributed depth first traversal algorithm will work. So, initially let us say 1 is the initiator. So, it will pick one of its neighbor, let us say that it picks up 2. So, it forwards the token to 2. Okay. Now, let us say 2 forwards the token to 3, 3 forwards it to 4, 4 forwards it to 5, right. 5 forwards it to 6. Now, then let us say 6 forwards it to 1. What does 1 see? That the token has come back along an edge for which the neighbor was not yet used. So, it finds that used 1 6 was false, but you have got the token from 6. So, what is it going to do? It will send the token back, right. What 6 going to do? It will choose some other neighbor. So, it will send it to 2.
So, what step will it do once it reaches 1?
When 1 gets the token, 1 will see that it has got the token from a neighbor which is not used.
In this document, if father is undefined.
Father of who is undefined? Father of 1?
For each process upon receipt of token, begin if father is undefined.
Now, for 1 father is defined, for 1 father is itself. Okay, the initiator, for the initiator the father is itself. So, its father is defined and it has got the token from some node which is not yet used. So, it knows that it has got the token along a frond edge of the tree. Okay, so, that the depth first tree is already there 1, 2, 3, 4, 5, 6. Now, this is a frond edge of the tree, right. Now, do you understand what is a frond edge? See, if you look at the depth first tree which has been traversed so far. So, from 1 we went to 2, from 2 we went to 3, from 3 we went to 4, from 4 we went to 5 and from 5 we went to 6. Okay. Now, from 6 to 1 this is a frond edge, because this is not a part of the tree, tree can never have cycles, right. So, you have detected a cycle. So, what is it going to do? It will send the token right back, all right. So, once the token comes back here, 6 will now forward it to some other neighbor, maybe 2. 2 will also do the same thing, because the token has come from a neighbor which is not visited, because used 2 6 is false, but it has got the token from 6. So, it will send it back, then 6 will send it to 4, it will send it back. Now, you see all of this is useless computation, and then the token goes back from 6 to 5, then 5 will send it to 1 and 1 will send it back, 5 will send it to 3, 3 will send it back, then 5 will send it, return it to 4, its parent. So, you see after every iteration there is a lot of token passing back and forth which is useless. And why is that happening? Because every frond edge is being traversed twice by the token, right. So, what is the complexity of this algorithm? 2e, right, because the token goes, right, and that is also the time complexity, because at a time only one token is moving. So, the time complexity is twice of e, which is a lot, right. So, now the first improvement that we will look at is called Awerbuch's improvement on the classical depth first. Yes.
So when 4 will get back message from 5, will it send to 6 or not?
When 4 gets that message from 5, it will not send it to 6, because 4 has already made used q to be true. See, when 4 gets the token from 6, at that time it will send the token back, but it will set used for 6 will be assigned to true. Okay. So, it will not send it along the same edge again, but all the same, you see, after you have gone from 1 to 2 to 3 to 4 to 5 to 6, your depth first tree is already discovered. All your token movements after that along those front edges are useless, right. If you knew that they were front edges, you would not forward the token through those edges, right. So, what Awerbuch's algorithm says is that why do not we do the following thing, that whenever before forwarding the token, I will inform my neighbors that I have the token, all right. So, let us see how that works in the same algorithm. So, in the same algorithm, let us see what we do this time. So, 1, 2, okay, the same network. Now, let us work on this with the new style of algorithm. So, when the token is forwarded from 1 to 2, what 2 will do is that it will inform all its neighbors that I have the token, right, and it will. So, this is going to be done by using a this message, this. Okay. What was the red one? It was the token message. This is a different message, okay. And these nodes, when they get the this, they will send back acknowledgements, ACK, all right. After it has got back all the acknowledgement messages, then it will forward the token to one of them. Now, what is the advantage of doing this? Advantage is that when the token comes at some later point of time to 4, let us say, then 4 knows that 2 is already visited, because the this message was sent from 2 to 4. So, it knows 2 is visited. So, it will not forward the token to 2. Okay. Similarly, when 6 gets the token, it will not send the token to 2 again, all right. Even 1 is going to do that. In the before 1 forwards the token, it will send its ACK along all these and get this along all these and get back all the ACKs, right. So, that when 6 gets the token, it will not send it to 1, because it know that 1 is visited already, all right. Now, let us understand that if we do this, what is the benefit that we are going to get. So, number of messages has increased, but let us look at the number of time steps. What is the number of time steps that we are taking? How many time steps is the token going to traverse? How many hops is the token going to do? N minus 1, right. So, the number of token messages is twice of n minus 1, right. So many token messages. Why twice? Because the token goes down the edges of the tree and then returns back along the edges of the tree, right. The token has to return, and the tree, the depth first tree has n minus 1 edges. So, each edge is traversed once from the parent to the child and once from the child to the parent. So, we have twice of n minus 1 token message, right. And how many vis and ACK messages are we going to have? 2e, but then how many time steps are we going to need for that? Before forwarding the token, I am having one round of vis and one round of ACK. So, if I look at the number of time steps, what is the number of time steps or the number of rounds? That is twice of n minus 1 for the token, and before sending each the token, we are having twice, once for vis and once for ACK. So, plus twice n, right. And what does this figure come to? 4n minus 2. Okay. This is the time complexity. So, the time complexity has gone down from what was the previous case, twice e. So, from twice e we are now down to 4n minus 2. The number of messages was twice e in the previous case. Now, how many do we have? Okay, let us differentiate between the two. Along the token edges, along the edges of the DFS tree, we are sending one vis, one ACK, one token downwards, one token backwards, right. How many such edges do we have? N minus 1. So, n minus 1 into 4 for these, right. And what about the front edges? Along the front edges, what are we going to have? So, vis from this side, ACK from this side, right. And also again when this one reaches here, you will have to send a vis from this side also. Why? No, why do we have to send the vis from this side? Because otherwise when the token comes back to 2, it will again send it to 6. So, not only is it necessary for 6 to know that 2 is visited, it is also necessary for 2 to know that 6 is visited, right. So, even 6 has to send a vis message to 2 when it gets the token, right. So, along the front edges we have 4, because in each direction one vis message and in the opposite directions one ACK message, right. So, 4 messages. So, along all edges we are having 4 messages. Along the tree edges we had 4, along the non tree edges also we have 4. So, the number of messages has jumped from 2e to 4e, okay. But this messages, some of them are in parallel, right. So, that is why the time complexity has gone down from 2e to 4n minus 2, all right. Okay. So, we are not strictly in a traversal algorithm, we are trying to use a combination of the wave, we are trying to relax the traversal algorithm requirements to gain more speed. All right. So, let us go through this algorithm once. So, this is Awerbuch's DFS algorithm. The algorithm prevents the transmission of the token through a front edge. When process P is first visited by the token, P informs each neighbor R except its father of the visit by sending a vis message to R. It is not necessary to send the father the vis message. Why? Father already knows that it is visited, father send the token to it, right. So, father definitely knows that the child is visited. So, there is no need to send the vis message to the father, and the forwarding of the token is suspended until P has received an ACK message from each neighbor. Now, when later the token arrives at R, at the neighbor R, R will not forward the token to P unless P is R's father, right. Okay. Awerbuch's algorithm computes a depth first search tree in 4n minus 2 time units and uses 4e messages, right. Now, is there any doubt about this algorithm? Yeah. So, that will actually reduce it by order of n, right, but well, it will reduce it by order of n, but if you do 4e minus order of n, then it remains order of 4e, right. So, because e is quadratic in n typically. Now, what about when later the token arrives at R, this one? Yeah. So, what is the objective of sending the vis message to R? To let know, so that R knows that P is visited already, right. So, if the token arrives at R, R will not forward the token to P again, right, because it knows that it is, but except when P is R's father. Remember that the node which sends the child sends the token, before it sends the token, it sends vis message to everybody, all its children, right, including the child to which it is sending the token. Now, the child which gets the token from the father has also got a vis message, but in the end it will have to send the token back, right. So, because that is the father, we make a special case for it, that we will send the token back after all the other children are visited. Okay. Clear? Now, there is a further improvement that we can do. Okay. First thing is that we are still forwarding the token only after the vis has been sent and the ACK has been received, then you are sending out the token, right. Now, Cidon made a further improvement on this, saying that why do we have to wait for the vis to go and the ACK to come back? Why do not we also forward the token at the same time, right. Now, see, so far whatever communication that we have done never required a FIFO channel, never required messages to be delivered in order, because the protocol was complete handshaking. I send a message, I get the acknowledgement and then I proceed, right. Now, I am saying that I will send the vis messages, I will not wait for the ACK. Before I get the ACK, I will forward the token. in you tell me, why do we need the ACK?
We know that the node knows it has been visited. If I send a viz message, I should know that the node knows that I've already been visited.
That the viz message has been received, right? If the viz message has not yet been received, then we can have a problem, and that is the problem which appears in Cidon's algorithm, and the algorithm applies a trick to solve that problem. First, let us understand what problem we are going to have if we just do this, that instead of waiting for the ACK to come back, in the same round as I am sending the viz message, I also forward the token, right. This is what can happen. Suppose I have a node P. The node P sends out the viz messages. Now, I have a node R, and the viz message is in transit, it is going towards R, right. Now, what happens is that the token, let me draw it with a different color. The token reaches R faster. So, the token has reached R already, the viz has not yet reached R. Now, what can happen? R can send the token to P along a front edge, precisely the thing that we want to avoid, right, that it has sent the token back to P along a front edge. It also sends its viz, it also sends its viz, it sends its viz to all others, to everyone in fact, right, and it sends the token back along the front edge, right. Now, that is not what we want. Now, what is P going to do about it? Now, P sees the following thing. P sees that, okay, I did send a viz message to R, I sent a viz message to R, but then R has now sent me the token. So, it is obvious that the viz message did not reach R, it did not reach R, that is why it has sent the token, right. But the viz message will reach R at some point of time, and then at that time R will realize its mistake. Okay. So, what P is going to do is P will treat this as a viz message. P will not treat the token as a viz message, it will not treat the token as a token message, it will treat the token as a viz message. It will behave as if R has sent it a viz message, right, and not do anything. Now, what is R going to do? When R finally gets the viz message, it realizes that I have actually sent the token along a front edge, but it knows that P is not going to tell anybody, right. P will simply treat it as a viz message, it is not going to tell anybody. So, what R does is it completely ignores the fact that it has sent a token message and simply generates the token and sends it to some other neighbor, right. Okay. Is it understood? When the R realizes that, when it gets the viz message, it realizes that the token was sent along a front edge. So, it behaves as if it never sent the token message, right, and sends the token to some other, sends a token message to some other neighbor, right. So, you see the number of the message complexity and the number of messages, but the time complexity has gone down. Why? Because instead of right. So, we are now having fewer number of things. Yeah. Now, let us go through the algorithm quickly.
Sir, in this graph which you made, if the Wiz message gets lost, the first one is.
Oh, we are not assuming anything will get lost. We assume that channels are reliable. At this level of abstraction, we will assume that channels are reliable, nothing is getting dropped.
But if you assume the Wiz message takes quite a long time to reach.
It may take a long time to reach, but it will eventually reach, right. And the time, that complexity that we measure is in the number of rounds of the message, and the amount of time that a round takes can depend on the amount of time for a message delay from one node to another, right. So, our complexity is measured in terms of that. In an algorithm, you can't do better than that, because you do not know what is the underlying network infrastructure on which your algorithm will run. So, you can only count in terms of the number of rounds, not the real time that each round can take. The classical DFS we already showed that it took order of 2e number of rounds. Where are we talking about trees? We are not dealing with trees, we are dealing with general graphs, networks. Okay. We are not dealing with trees. Trees will be special cases of this, which we are not doing right now. Okay. So, Cidon's DFS algorithm is like this. The token is forwarded immediately. The following situation is important. Process P has been visited by the token and has sent a Wiz message to its neighbor R. The token reaches R before the Wiz message from P, and in this case R may forward the token to P along a front edge. Okay, this is precisely the problem that we talked about. And the situation is handled as follows, that process P records to which neighbor it most recently sent the token. Normally, it expects to get it back from the same, right. If it gets it back from some other neighbor, it ignores the token, but marks the edge RP as used as if it received a Wiz message from P. When R eventually receives the Wiz message from P, it behaves as if it never had sent the token to P. Okay, that is how we handle this. Now, what is the time complexity? It is 2n minus 2. How do we get this figure? Yeah, so the token actually moves n minus 1 number of times, okay, and we are not waiting for the ACK and Wiz messages before forwarding the token, right. So, the token moves for consecutively for n minus 1 time steps. So, and then goes back, okay. So, it goes back along each of those edges. So, twice of n minus 2 time units is what we need in total, and we use 4e messages. Why? Same this thing as before, and even for the cases where the edges where the token was sent along the front edge, what happens to those edges? Okay, there is a Wiz message that is sent from the other side. From this side, the token is interpreted as the Wiz, right, and both sides send the ACKs. Okay, so, again we have 4 number of messages, right. Now, what I will ask you is to figure out why do we need ACK messages here at all, right. So, or do we at all need it? All right. I want this you to think about this answer. and let me know. Alright. In this Cidon's DFS algorithm, do we need ACK messages? If so, why? Okay. Yes. Channels may or may not be FIFO. Why do you need FIFO channels here? It's not required.
But channels are reliable.
Channels are reliable. Yes. All channels are reliable.
Nodes will get the visit. The acknowledgement is that the visit is received. So if you send the visit, it will reach the node, the reliable channel.
It will receive. It will reach the. Every WIS message will eventually reach, and if the node sends an ACK, then that will also be reached on this side. Right. Now the question I am asking you is, in this algorithm, do you need the ACK messages? If so, why? If not, then I mean, what is the justification that for the fact that you don't need it? Okay. Now, yes.
Along the front edge, in the token along the front edge, is that number of time units not increase?
No, because you see, if you knew that it was visited, you would have sent a WIS message, right? So it is interpreting that WIS message as a the token message as a WIS message.
Anyway take if you go along the actual tree edges.
Yes.
If you send it on the front edges, that is something extra.
No, because you are masking that by saying that that was not a token message, that was a WIS message, and both of the sides agree to it that it's a WIS message. The receiver of that message.
Yeah, messages will remain same. Has to wait. That time unit has wasted.
But I have to wait till the next token is generated.
Yeah, actually, you see, you have to see there is a little bit. The thing here is that we are assuming that the WIS message takes more than one cycle, more than one time unit to reach. Right, that's what is creating all the problem. If it was reaching exactly in the next cycle, then this case can never happen. Right, so the WIS message is taking longer than that. All right. Now, what we have not discussed in more detail here is that what do you define as the time of a round? It is the time that the maximum transmission delay of a message from point A to point B, right. That is the duration of the round. That is how, if you do it that way, then you will see that you will again get back to this result, right. Otherwise, you see, if you do not do it that way, then you will not be able to create this situation. If you assume that they all are synchronized and they all take exactly one times unit to be delivered, then this situation will not happen. So, in previous case also, you see, when we talked about that you are sending WIS messages to your neighbors and getting back, see, they are neighbors. So, this is the time delay from a node to its neighbor. All right. So, that time you have to accommodate.
It also sends a WIS.
It also sends a WIS.
So there are actually two WIS reaching P from out.
Right. Oh, it will ignore the other one.
So what would be 5E instead of 4E? There's extra message.
No, the token is not sent, you see.
Yeah, but for that WIS.
Okay. So what you are saying is that there is one WIS from this side
extra.
one whiz from this
It
side.
will not send, does it send a this message again, sir? If it has
No,
already
now
sent
now
it,
you answer me one question.
The
Will
node
it
that
send
is-
the ACK?
Yes.
So once you answer the question that whether the ACK messages are needed and whether you will send them and whether you will send them always, so think about that and let me know what you feel about that. All right. Okay. So that's what we had to say in this wave and traversal algorithms. I also strongly urge you to take a look at Gerard Tell's book for several other variants of these wave algorithms. We just studied echo algorithm as a pure wave algorithm and then looked at the subclass of traversal algorithms and looked at these algorithms like depth first traversal and their improvements, right. There are whole lot of other wave algorithms also. Take a look at them, and when we study deadlock detection, when we study other election algorithms, we will revisit these wave algorithms and we will see how we can use them to solve this. By the way, the termination detection algorithm that we studied, is that also is that also a wave algorithm? It's also a wave algorithm, right, because it's actually that the messages are going out and then the weight is getting collected and brought back. So if I ask you, for example, that using the echo algorithm, can you collect the IDs of all sites in the network, okay, or if every node has some weight, maybe some balance that is stored in the branch of that bank branch, okay, can I use a wave algorithm to find out the total balance for all nodes in the network, right. Now you know you will need a global snapshot detection algorithm and you will also need an algorithm to collect this information from all the nodes, right. So you have studied how global snapshot detection can take place. You have studied how you can collect information or distribute information using a wave algorithm, right. Can you combine the two over an echo algorithm and compute the a stable balance of the sum of the balances of all the branches in the network? Did you get the problem, right? With what you have studied, you should be able to use these algorithms, combinations of these algorithms to solve that problem, right. So these are the types of questions that I may ask in your exams, that these are the basic algorithms that you have studied, okay, like termination detection, like snapshot collection, like this echo, depth first traversal. You should be able to solve real world distributed problems using combinations of these algorithms. Otherwise, there is no point in learning those algorithms, right. So you should be able to tweak those algorithms and solve these things, okay. We will have more discussions on combinations of these things in due course of time. Thank you.